Calculate the molar mass of sodium. Sodium, being a single element, is just going to be the mass from the periodic table. Sodium's mass off of the periodic table is just 22.990. But this is going to be a conversion factor. So I need to make sure that my molar mass is represented in such a way that I can use it inside of dimensional analysis. So the first version of the ratio I will write is for every 22.990 grams of sodium, I have 1 mole. And the second conversion that I will write is for every 1 mole of sodium, I have 22.990 grams of sodium. Given 2 sodiums reacting with 1 chlorine, forming 2 sodium chlorides, create the multiple ratios between sodium and sodium chloride. I'm going to identify the molecules of interest as sodium and sodium chloride. They're given inside of the problem, and I am emphasizing them and visually connecting them in the equation. Then I will create the multiple ratio, pulling the coefficient from in front of sodium, which is 2, inserting the word mole, and then putting the formula for sodium, which is just Na. And I will say that I have 2 moles of sodium for every coefficient in front of sodium chloride, 2, inserting the word mole, formula for sodium chloride. And since this is a conversion factor, I will flip the fraction and say that for every 2 moles of sodium chloride, there are 2 moles of sodium. Calculate the molar mass of sodium chloride. First up, I need to go ahead and write down everybody that's present. That's going to be sodium and chlorine. Then I will reference the formula to find out how many of each I have. I will look at the subscripts to do so. Sodium has an invisible subscript, so that means I have 1 sodium, so I will just take the mass of sodium directly off the periodic table. Mass of sodium from the periodic table is 22.990. 1 times anything will be itself, so 1 times 22.990 will give me 22.990. Chlorine has an invisible subscript, so that means I only have 1 of them. 1 times the mass of chlorine from the periodic table. The mass on the periodic table is 35.453. One times 35.453 will give me 35.453. I will add those up. And that will give me 58.443 grams of sodium chloride for every 1 mole of sodium chloride. Since this is a conversion factor, I will write both versions. And the flipped version would be for every 1 mole of sodium chloride, there are 58.443 grams of sodium chloride. If 7.92 grams of sodium react, how many grams of sodium chloride will be produced? I'm going to go ahead and translate this English problem into math. I will find the question word. The question word is how many, so that is going to translate to X. Grams, compound attached is sodium chloride, will be produced is my equal sign, and then the number given in the problem. You'll notice that the number given in my problem is surrounded by brackets. This is because the number can be different for you, but the steps that I'm going to take are going to be the exact same. So my number given in the problem was 7.92 grams sodium. Then I'll go ahead and set up my dimensional analysis train track. Now, I currently have grams of sodium in the numerator, so I need to find from the 3 conversion factors that I have already found in previous questions, which has the grams of sodium in the denominator. That is going to be the molar mass of sodium, and the red version is going to have grams of sodium on the bottom. So that is what I will plug in. Grams of sodium would then cancel, leaving me with moles of sodium. I don't want moles of sodium, I want grams of sodium chloride, so I'm not quite done. Now I need to get out of moles of sodium. I cannot use the same conversion factor twice. The only other conversion factor that has moles of sodium is going to be the mole-to-mole ratio. The version of the conversion factor that has moles of sodium in the denominator is the red version, so that is the version that I will use. Moles of sodium will cancel, leaving me with moles of sodium chloride. That is not the unit that I wanted, however. I am close. I want grams of sodium chloride, not moles of sodium chloride. So I need a conversion between moles and grams of sodium chloride. This is going to be the molar mass of sodium chloride. I currently have moles of sodium chloride in the numerator, so I will need to choose the version that has moles of sodium chloride in the denominator. That is going to be this blue version right here. So that is what I will plug in. Moles of sodium chloride will cancel. That will leave me with grams of sodium chloride, which was the unit that I said that I wanted. So that means I can go ahead and start solving the problem and plugging it into the calculator. This is going to happen by me multiplying everything that is in the numerator and dividing by everything that is in the denominator. So that means I will have 7.92 times 1 times 2 times 58.443 divided by 22.990, 2, and 1. That will give me the number 20.13347368. On blend, I want 2 decimal places, 1, 2. So this first 3 is the last number that I care about. I'll look over to see if I need to round up. 3 does not make me round up, so that means that my final boxed answer would be 20.13. Only English left in my math. The thing that I said that I wanted, grams of sodium chloride, would be my final boxed answer. Calculate the molar mass of trinitrogen heptoxide. First thing I'm going to do is I'm going to go ahead and identify everybody that is present. That is going to be nitrogen and oxygen. Then I will account for how many of each I have. Nitrogen, I have a subscript of 3, so that means that I have 3 nitrogens. Oxygen, I have a subscript of 7, so I have 7 oxygens. Nitrogen's mass from the periodic table is 14.007. 3 times 14.007 gives me 42.021. Oxygen's mass from the periodic table is 15.999. 7 times 15.999 will give me 111.993. When I add these up, I get 154.014 grams of trinitrogen heptoxide for every 1 mole of trihydrogen heptoxide. Since this is a conversion factor, I'm going to go ahead and flip it just in case I need it in the other direction. So I will say for every 1 mole of trinitrogen heptoxide, I have 154.014 grams of trinitrogen heptoxide. Given 3 nitrogens being added to 7 oxygens going to 2 trinitrogen heptoxides, create the multiple ratios between trinitrogen heptoxide and nitrogen. I will identify the molecules of interest from the problem and underline them in the equation. Once I have done that, I will go ahead and visually connect them before creating the multiple ratios. To create the multiple ratios, I will reference the coefficient in front of each compound. Coefficient in front of nitrogen is 3. I will insert the word mole and then put the formula for nitrogen. Then I will compare it to the other compound, which is going to be the trinitrogen heptoxide. Coefficient in front of trinitrogen heptoxide is 2. I will insert the word mole and then put the formula for trihydrogen heptoxide. Since this is a conversion factor, I will go ahead and flip the conversion. And instead of saying for every 3 moles of nitrogen, I have 2 moles of trinitrogen heptoxide. I will say for every 2 moles of trihydrogen heptoxide, I have 3 moles of nitrogen. Calculate the molar mass for nitrogen. First up, I'm just going to go ahead and establish how many I have and who I have. Nitrogen is made up exclusively of just nitrogen. However, I do have a subscript of 2, so I will need to multiply the mass from the periodic table. Nitrogen's mass from the periodic table is 14.007. Two times 14.007 gives me 28.014. And this is a conversion factor, so I am going to go ahead and make sure that my variables are in such a way that I could use it directly in a dimensional analysis problem. So I will say for every 28.014 grams of nitrogen, I have 1 mole, or for every 1 mole of nitrogen, I have 28.014 grams of nitrogen. If 5.74 grams of trinitrogen heptoxide are produced, how many grams of nitrogen reacted? First thing that I'm going to do is I'm going to translate this English problem into math. I'm going to find the question word, how many, and translate that to x. The question word was attached to the unit grams, and the molecule attached was nitrogen. R produced is my equal sign, and then my number given in the problem is 5.74. You'll notice that my number is within brackets. This is because my number may be different than yours. However, the steps that I am going to take to solve this problem are going to be the exact same as the steps that you would need to take to solve your problem. Once I have my number, variable, and compound plugged in, I will go ahead and create my dimensional analysis train track. I will then begin to solve the problem using the conversion factors that I have already discovered from previous problems. Currently, I am in grams of trinitrogen heptoxide. I need to find the conversion factor that allows me to cancel out grams of trinitrogen heptoxide. This is going to be the molar mass of trinitrogen heptoxide. That is going to be this conversion set. I'm currently having grams in the numerator, so I need grams in the denominator. That is going to be this red version, so that is what I will plug in. grams of trinitrogen heptoxide will cancel as they appear in the numerator and in the denominator. I am currently in moles of trinitrogen heptoxide, and I want grams of nitrogen. I am not in the correct molecule, so I need to get out of that. I've already used the molar mass, so that means that it would be inappropriate to use it again. I am going to have to use the mole to mole ratio. I am going to choose the version of the mole to mole ratio that will allow me to cancel trinitrogen heptoxide. This is going to be the version that has that in the denominator. That will be my red version here. Moles of trinitrogen heptoxide will cancel out, leaving me with moles of nitrogen. This is not the unit that I want, however, it is the correct molecule type. So that means that I am very close, and all I need to do now is choose the conversion factor that will allow me to get from moles to grams. This is going to be my molar mass of nitrogen. I need to choose the molar mass of nitrogen conversion factor that has grams in the numerator, as I currently have moles of nitrogen in the numerator, and I need to cancel it out. That is going to be my black version here. Moles of nitrogen will cancel as they appear in the numerator and in the denominator. The only English left in my math is grams of nitrogen, which is the unit that I stated that I wanted in the beginning, so that means that it is appropriate to go ahead and solve the problem. I will solve the problem by multiplying everything that appears in the numerator and dividing by everything that appears in the denominator. So that means I will have 5.74 times 1 times 3 times 28.014, and I will be dividing by 154.014, 2, and 1. This will give me the number 1.56604949. Blend asks for 2 decimal places only, so the first 6 is the last number that I care about. I'll look over to see if I need to round up. 6 does in fact make me round up, so that means that my final boxed answer would be 1.57. Only English left in my math, grams of nitrogen. Calculate the molar mass of aluminum sulfate. The first thing that I'm going to do is I'm going to list out all of the members inside of the compound. This is going to be aluminum, sulfur, and oxygen. Next, I will look at the subscripts to check how many of each I have. Aluminum has a subscript of 2. Sulfur has a subscript of 1, however it is being multiplied by this 3. 1 times 3 is 3. Oxygen has a subscript of 4, but it is being multiplied by 3. 4 times 3 is 12. Aluminum's mass from the periodic table is 26.982. Two times 26.982 gives me 53.964. Sulfur's mass from the periodic table is 32.066. 3 times 32.066 gives me 96.198. Oxygen's mass from the periodic table is 15.999. 12 times 15.999 gives me 191.988. Whenever I add all of these up, That will give me my molar mass of aluminum sulfate. When I added those up, I got 342.15. This number needs a unit. The unit for molar mass is grams per mole. I'm going to write it in such a way that it is easily used in a dimensional analysis problem. Since it could be used in a dimensional analysis problem, I will write the molar mass as a conversion factor flipped so that I can have access to both versions if I need them. This effectively gives me that 1 mole of aluminum sulfate is equal to 342.15 grams of aluminum sulfate. Given aluminum sulfate being added to iron 2 phosphate, producing 2 aluminum phosphates and 3 iron 2 sulfates, create the multiple ratio between aluminum sulfate and aluminum phosphate. The first thing that I will do is I will identify the molecules of interest. They are given in my problem, and I will underline them in my balanced chemical equation. Then I will visually connect them, and I will create the multiple ratios. I will do so by taking the coefficients in front of each and assigning a ratio. The coefficient in front of aluminum sulfate is an invisible, which makes it a 1. So I will write 1, the word mole, and then aluminum sulfate. The coefficient in front of aluminum phosphate is 2, so I will write 2 moles aluminum phosphate. Then, since this is a conversion factor, I will write them as the reverse. And I will say for every 2 moles of aluminum phosphate, there is 1 mole of aluminum sulfate. Calculate the molar mass of aluminum phosphate. The first thing that I will do is I will write out everybody that is present. That is going to be aluminum, phosphorus, and oxygen. Next, I will check to see how many of each I have. Aluminum has an invisible subscript of 1, so that means I have 1 aluminum. Aluminum's mass from the periodic table is 26.982. 1 times anything will give you that same number. Phosphorus has an invisible subscript, so that means that I only have 1 of them. Phosphorus's mass from the periodic table is 30.974. 1 times 30.974 will give me 30.974. Aluminum has a subscript of 4, which means that I have 4 of them. Oxygen's mass from the periodic table is 15.999. 4 times 15.999 gives you 63.996. When I add all of these up, I will get 121.952 grams of aluminum phosphate for every 1 mole of aluminum phosphate. And since this is a conversion vector, I will write the reverse, that for every 1 mole of aluminum phosphate, I have 121.952 grams of aluminum phosphate. How many grams of aluminum phosphate are produced if 3.97 grams of aluminum sulfate react? First thing that I'm going to do is I'm going to translate this English problem into a math problem. I will do so by changing how many into x grams of aluminum phosphate are produced if is my equal sign, and then my number given in the problem, which for me is in brackets. This is to signify that my number may be different from yours. However, you will be able to solve this problem the same way that I do, as the steps are the exact same, excluding the number that I have for my mass of aluminum sulfate. Once I have everything plugged in, I will go ahead and create my dimensional analysis train track. From here, I can go ahead and solve the problem utilizing the conversion factors that I have already discovered in previous problems. Currently, I am in grams of aluminum sulfate. I need to remove grams of aluminum sulfate from my problem, so I need to use the molar mass of aluminum sulfate. I currently have it in the numerator, so that means I need to choose the version of the molar mass of aluminum sulfate that has grams of aluminum sulfate in the denominator. That is going to be my blue version here, so I will go ahead and plug that into my equation. Grams of aluminum sulfate will cancel as they appear in the numerator and in the denominator. Now I can go ahead and cancel out moles of aluminum sulfate. It would be inappropriate to choose a molar mass calculation again, as I have already used that conversion and that would get me back to my starting place. So I am going to have to use the mole to mole ratio between aluminum sulfate and aluminum phosphate. Currently I have moles of aluminum sulfate in the numerator, so that means I will need to choose the version of the mole to mole ratio that has moles of aluminum sulfate in the denominator. That will be my red version here. Moles of aluminum sulfate will cancel as they appear in the numerator and in the denominator. Currently, I have moles of aluminum phosphate in the numerator. However, my stated desired unit was grams of aluminum phosphate, which means that I have not quite finished my problem. I currently need to get from moles to grams, which means that I need to use the molar mass of aluminum phosphate. I will now choose the version of the molar mass conversion factor that has moles of aluminum phosphate in the denominator such that they cancel. That is going to be my red version. I did not leave myself enough room for the entire thing to fit on one line. I will move aluminum phosphate above to accommodate this. Moles of aluminum phosphate will cancel, leaving me with grams of aluminum phosphate, which was the unit that I said that I wanted in the beginning, which means that I can now go ahead and solve the problem. I will be multiplying everything that is in the numerator, so I will have 3.97 times 1 times 2 times 121.952, and I will be dividing by everything in the denominator. So I'll be dividing by 342.15, 1, and 1. When I do that, I get the number 2.830042.028. Blend stated that I wanted 2 decimal places, so this 3 is the last number that I would care about. I will look over to see if I need to round up. 0 does not make me round up. So that means that my final boxed answer would be 2.83, only English left to my math, the unit that I said that I wanted, grams of aluminum phosphate.